Okay, let's get started. Good afternoon. Welcome to CAM Logic's Tech Tuesday webinar series. As I mentioned, my name is John Gaioni. I'm the Director of Marketing for CAM Logic. We are located in Oxford, Michigan. Joining me today and actually presenting is Brant Ross and Nelson Wu of Motionport. Motionport is our Siemens business partner supporting us in Femap. Our webinar today is entitled Correctly Assessing the Structural Integrity of Product Components Using Femap. Before I turn it over to Brant, I just want to give you a little background on CAM Logic. CAM Logic is a leading provider of product lifecycle management solutions, 3D scanning and rapid prototyping technologies and services that help companies design and build better products, improve their processes, reduce costs, and maximize profitability. We provide unparalleled 3D engineering technological software solutions along with the services and support to ensure our clients' successes. We have over 16 years of CAD/CAM CAE expertise. We have world-class software partnerships, cutting-edge hardware products, and pride ourselves on the fervent focus on understanding our clients' processes, needs, methodologies, and unique challenges in order to provide real solutions. We are a full-line Siemens PLM partner offering the entire PLM software suite, which includes NX, Solid Edge and the Velocity portion, Team Center, and Femap. We strive to be your engineering technology partner of choice, and we look forward to the opportunity. And now I'm going to turn over the webinar to Brant Ross of Motionport.
Hello all. Yes, my name is Brant Ross, and my background is in mechanical engineering. I have a PhD degree, and also presenting today will be Nelson Wu, who will be conducting the demo portion of this webinar. He's also a mechanical engineering expert with a master's degree, so we look forward to presenting this information to you. In contrast with CAM Logic, our focus at Motionport is focused on computer-aided engineering, which may include structural analysis, which we'll talk about today. We also engage in motion simulation and multi-body dynamics. We have abilities to look at control system design and also heat transfer analysis. So these capabilities mesh in very well with the overall large PLM activity of CAM Logic, and that's why Motionport and CAM Logic work together to serve our clients, our joint clients. Today's topic is that of assessing structural integrity of components. So I'd like to start out by asking the question, why do we want to assess structural integrity of these components? And there's a variety of things that we can be concerned about. First of all, we want to be able to test in advance of putting a component into production whether or not there is any possibility for sudden failures. So this the sudden failure may occur when loading conditions cause stresses at a given location to exceed the yield stress. And then plastic deformation can occur, and then that can lead to a sudden failure. Second thing is durability testing. A component may be undergoing cyclical loading, and one would want to look at the magnitude of the cyclical loading and then apply the proper factors to determine whether or not there could be some failures at a later date. Those failures could involve cracking, and it's possible that the geometry of a component could have sites that could initiate cracking, areas where there could be stress concentrations. So that would be carefully examined in order to assess structural integrity. On the positive side, when the structural integrity is assessed, then you can see areas of high and low stress. And in those areas of low stress, it's possible to remove material and still maintain structural integrity. So that would be a technique to be able to reduce weight of a component while maintaining performance. When doing so, it's important that a multitude of load cases are considered to make sure that in a given area that may have low stress in one load case may have a higher stress in a different load case. So that's why it's important to look at all the load cases of interest for that component. The last area is that of vibrational analysis, looking and testing for vibrational frequencies. So if you know what the vibrational frequencies of the component might be, then you can compare those frequencies with the frequencies that the overall product is going to experience. And when there is a match in the frequencies, then you know that you will have this excitation of the component that can lead to higher forces and will contribute to failure. And so an issue of structural integrity is to make sure that vibrational frequencies at the component level are not in the same range as frequencies in the system during operation. And there are ways to add material and remove material in order to adjust the frequencies. Okay, so once we've decided to assess structural integrity, the question is, what kind of inputs do we need? So the first input that's needed is geometry of the component, typically solid geometry. Second is you need to have input loads, and as we mentioned earlier, it may be important to have multiple input loads to assess different operating conditions that that component may undergo during operation. And the third item that's needed as input is material properties. So that would be basic modulus of elasticity for a given material, Poisson's ratio, and yield stress are all things that you would want to know in order to be prepared to do this assessment. So what's the process to assess structural integrity? First of all, you need to obtain these items from the previous slide, the geometry, material properties, load cases. Second, you want to create a finite element mesh from the geometry. What this will do is subdivide the geometry into small, evenly defined blocks of material that equations can be associated with. So this is the method for the solution. We take complex geometry and we build up that geometry with basic bricks or tetrahedral type shapes as needed in order to correctly define that geometry in all its detail, but using very basic shapes. Okay, the next step is to then apply the material property definition to that model, apply the loads, and by the way, the loads are not only applied forces, but part of the load definition is also defining how that geometry is constrained in space. So you will apply certain loads, you will have certain attachment points, there will be reactions where the geometry is attached or fixed. Okay, then once you have all those inputs, then you will run the simulation, and then the next step is to review the results and then revise the analysis as necessary. So in other words, there are ways to look at the output of the analysis and come to a conclusion as to whether or not all the definition and all the process that was followed, whether that was done correctly for that particular component. If there is a need for some adjustment, then you'd want to go back and revise the analysis, repeat the solution process, review the results again until you were satisfied with the results. And by doing this process and the checking, then at the end of the task, you would be able to define or refine a definition of best practices for the structural analysis of that kind of component. So in other words, any time that you have simulation results that you're not happy with, but you were following the best practices that you knew about, then that's new information, so it's good to add that into the intellectual property, really, of your organization by refining those best practices so that the next time that such a component is analyzed, that a better technique can be followed. Okay, so we've reviewed the issues around assessing structural integrity. Now the question is, how do we do it in an efficient way? And the answer to that is we need to use software that will help us perform these tasks. So the software that we are going to look at today is Femap. It's a product that we provide with CAM Logic to clients, and it is compatible with the NX software environment, but also with other software as well. So what does Femap help us do? First of all, it helps us with this task of the mesh creation from geometry. Second, we can then apply this information we have on material properties and the load cases, both applied loads and the constrained locations. Loads can be things like point loads, but also things like pressure on different faces of the geometry. And the powerful thing is that when we apply these conditions of the load cases, we are doing so from a geometry point of view, so that later if we decide to change the mesh, these applied load conditions do not have to be readjusted because they're defined with respect to the geometry, and then they're applied to the little finite elements that are created automatically. And by the way, if we look at the graphic here, the second figure along the bottom, and we see all these little lines and subdivisions, this is what we're talking about with these finite elements. So the geometry is subdivided into these small, simple style of building blocks that can then cover all the material in the part, and then that's how our calculation is done. Femap features an embedded NX Nastran solver. So Nastran is an industry-known solver for structural analysis. It's very well known, so that when you use this solver, people will be very content with the results and know that they're accurate because of the long usage of Nastran and its good reputation. And then finally, Femap has capabilities to review and support the documentation of results. You can interactively review results, and these figures along the bottom are examples of depictions coming from Femap. And those depictions can then also be exported into a document that will also contain information about all the different analysis assumptions you made, so that you can retain all that information. And it's so basically Femap can help you generate a report of the work that you did. Okay, so how does Femap help the user be able to do this meshing? So first aspect is usability. So Femap is set up with all the tools very focused on the structural analysis. And as you see here in this graphic, it's explaining all the different aspects it has. There's a model tree that contains a hierarchy of everything that you're working with, makes it very easy to access information. And as you work with specific aspects of your model, it shows this entity editor will show you all the details and dynamically update itself, provides feedback on what's happening during the process, and you can also call up data. It has the ability to look at multiple models. Toolbars are customizable, and you get feedback during analysis. And this thing here towards the right, lower right, it says Interactive Meshing Toolbox. This is really important because there's automatic meshing capabilities, but then sometimes there's a need for some small adjustments. And this Interactive Meshing Toolbox is very powerful, and we'll see more information about that with the demo. So here's a comment from one of the users saying that the tutorials were easy to use, everything was intuitive, following kind of a Windows standard way of working with software. Okay, Femap also supports geometry processing. Sometimes the geometry that comes from the CAD system has some problems with it with regards to meshing. Has to do with like edges that may not connect up properly, and therefore the definition of surfaces and so forth isn't quite correct. So Femap can automatically take care of these issues, clean up the geometry, and prepare that geometry for meshing. The The interactive meshing toolbox is used to resolve problems once they're identified. So these graphics show some different examples of issues. For example, the CAD model may have a multitude of curves defining what really should be a logical edge. So that's why here in the upper right it talks about combined composite curves. You can combine the curves from CAD so that things are more logically laid out to have a very nice and effective mesh. Could be little short edges here in the upper left. It shows a little edge here. You don't want that to be the basis for meshing, so again, you can combine that with nearby curves in a logical way. Lower left, it's showing this notion of slivers. You can have these little tiny surfaces, and again, you want to merge those with nearby surfaces, and so that's the solution here in the lower right, combine boundary surfaces so that you can simplify the geometry from CAD so that it is in good shape to be meshed efficiently. Some other things that you may need to do is split up geometry in order to have logical patches for meshing, offset some curves so that you can control the quality of the mesh around certain features. Here in the lower left, it gives us an example of this mapped meshing around the hole so that there's a nice transition between the circular features and the more rectangular shape of the geometry around it. So these are all detailed features that come up and are available so that when you need them, you can quickly resolve things. With some models, the material tends to have a thin shape. And so it may come in from CAD as a solid model, but what you really want to do is take that solid model information and use that to define what we call a thin wall type of model, and we can represent that geometry with a flat set of shell elements, and those shell elements need to be located in the middle of the solid geometry. And there's nothing defined there by the CAD system, but Femap can take that solid geometry already or automatically create that midplane so that you can do that fast conversion to the shell elements and then help you connect up the midplanes with other midplanes. And then as you see in this model where we have a thin-walled part that's undergoing certain loads, again, the representation, the proper representation of shell elements, and then that can be handled very well. You can see what the shell elements are shown in the lower right as compared to trying to do the solid, trying to do it with the solid model on the left. And you can see that the shell model has a more even appearance. You can use four-sided elements, and the number of nodes is much reduced, so the degrees of freedom to solve the model is reduced. So the bottom line is it's a less complex model, but you can get greater accuracy in the results, and so it's important that Femap supports this midplane extraction. Some other advanced capabilities can include assembly modeling. So in other words, having multiple structure components that interact with each other. They may need to be glued together at certain locations, or they may need to have some kind of contact so that they can apply pressure between each other. And the other advanced technology is the interactive meshing capability. So for assembly modeling, it's important to represent the structure interacting as it truly does in use. And so sometimes these components are pushing against each other and sliding. So if it was just a case of things being exactly matching each other, say they were welded together, that would be one thing. But with the sliding is when you want to be able to define things with contacts. And to be able to do this properly then means that you can have accurate results that reflect what's going on during the application of the loads and how the loads are passed along from one component to the next. So to support the assembly modeling, then what you need is a set of high-quality ways to assemble the different components with each other. So Femap offers linear, nonlinear contact. You can have friction. You can have glued connections. There's automation, definition of the contact, and then another specialized way to connect up multiple parts is the use of bolts, and that involves certain assumptions in order to do it very efficiently and accurately. So those techniques are supported directly in Femap. The one example they show here on the lower left is that of a hood of a car or a truck, and the idea there is that you have a certain frame that's supporting the sheet metal, but the interaction between the two can involve contact rather than, there might be certain locations that are welded, but much of the interaction is a straight contact. So here's feedback from one of the users, just saying how important it is to work with complex geometry, let the components interact with surrounding geometry, and having ways to define the interaction in an accurate way. Okay, so the next advanced area is this meshing and the interactive meshing. There's also issues of mesh quality. So you want the mesh to have well-shaped elements. You can check the quality of the elements, which has to do with their shape. And so then finding the bad elements can be difficult if you have a very complex element and maybe you have hundreds of thousands of elements. So the software needs to help resolve that. So there is a way to check that out, and we'll see more about that shortly. We want to be able to define different types of meshes. So there's this quad meshing, as you see here. Tetrahedral meshing is a way to do things in a very automated fashion. And then finally, to do hex meshes of solids can improve efficiency, requires some manual activity, but depending on the component, may be a very good approach. And then as you create the model, you want to be able to verify the quality of the mesh, and the red elements here indicate locations where the elements did not pass the quality test, or there are ways to go in and resolve that, and we'll see a little bit of that shortly. So again, with the meshing, then it's really important to customers to be able to develop these meshes quickly and efficiently. So at this point, I'm going to turn things over to Nelson to give us a brief demo and show us a few of these features that have been mentioned. So Nelson, let me pass along the screen to you, and you can take over. So we're just now waiting for Nelson. He will accept the change here of control, but it takes a second for the things to update.
Hopefully everybody's seeing my screen at this point.
Yeah, I'm seeing it now, so it should.
Oh, okay. All right. So I'm going to go ahead and show, this is sort of a complex geometry model that we meshed, and what you're seeing is that most of the geometry are plates of varying thicknesses. So what we actually did for this example is to create a mid-surface, and that's kind of represented by the these turquoise lines that are sort of in the mid-surface of these plates. And then we went ahead and meshed them. If I turn the geometry off and let's see. And now you're seeing basically these are our plate elements. And then I can go ahead and show some results here. You're basically seeing contour plots of von Mises stress. And there are certain areas that are, if I go to a different part of the model, you'll see that there are areas up here which show a lot of stress, and I'm going to rotate the model a little bit so that we can take a better look at things. The other nice thing about viewing the results in Femap is that you can deform the model So I can, this will kind of show what the model will look like when it's under certain loads. But the one thing here is that I've scaled the deformation by a scale factor of 2,000. So actually the structure is quite stiff, but we're still able to sort of gain some intuition as to how the model really deforms on a very small scale. But here we can, we can see it exaggerated to help us understand how to improve the design. And so we're looking at something here where this is where a lot of the load is applied to this white line, which is sort of representing a beam, or basically a structural beam. And then because it's pulling down, there's a lot of stress here. So and let's see, that was an area of high stress. If we go down to the bottom here and take a look at, this is the bottom of the structure, and while you don't see a lot of high stress, you do see a lot of deformation of the structure. And what we can actually do is we can also animate it. And I'm hoping that this will sort of show up through the webinar, but hopefully you should be seeing the model actually move. It's an animation of the model as it deforms.
Yeah, it's working.
Okay, great. So that was just a quick demo of how you can actually see the mesh within Femap itself. So I guess at this point I can turn over the presentation to Brant or John.
Okay, so let me bring my screen up again. Okay, so hopefully the PowerPoint image is back up. So I just want to really conclude here mainly with this slide. With the question is like, okay, what is your plan to increase your ability to assess structural integrity? So today we've talked about some important issues for doing this assessment. The importance of having an easy-to-use, intuitive user interface to be able to, do this meshing process, apply all the information, be able to use an industry standard solver to do the analysis, and then to be able to review the results. And also the importance to have software that is able to get into the very advanced topics, so that as you need more functionality, that functionality is available. Even though you may not use every advanced feature every time, it's important that it's there so that you don't run out of capability. And Femap does interface very well with a wide variety of CAD software, and so then it makes it quite easy to interact with the design process and to be able to take geometry and even do updates and have that pass on through to the mesh results. So we've presented today what this basic challenge is to do structural integrity, tools that exist to take care of it. There is logical follow-up types of things that can happen. This webinar itself will be available on YouTube. And the other thing, though, is if you wanted to contact either CAM Logic or Motionport, we can follow up with a maybe individual go-to meeting and be able to show some of these things and be able to answer your individual questions. So here you see some of the contact information, both for John at CAM Logic and then also Motionport. I mean, you can follow up with Nelson, and we can do some follow-up there, or contact John, either one here. And so John, do you have any closing comments?
Just want to thank everybody for coming tonight or this afternoon. And again, if you have any questions whatsoever, feel free to contact either company, and we'd be happy to help you out.
Okay, well, thanks everyone for your attendance, and we look forward to hearing from you. Thank you.